In this lecture series, you will be introduced to Sylow theorems. We will first discuss some prerequisites required to prove the Sylow theorems. Then, we will prove the three Sylow theorems using conjugacy classes, and finally, we will look at some applications of Sylow theorems. Let us define the center of a group G. The center of a group G is defined to be the set of all those points which commute with every other point in the group. We denote the center of the group G by Z of G. Therefore, Z of G is the set of all G in G such that G of X equals X times G for every X in G. We can make a few observations regarding the center of G. First, the center of an abelian group will be the group itself. We can also see that the identity element is always going to be in the center of the group. Now, we should ask ourselves a few questions. 1. Is Z of G a subgroup of G? And 2. If Z of G is a subgroup of G, is it a normal subgroup of G? You can pause the video here and try to answer these questions. Let us prove that Z of G is a normal subgroup of G. To prove that Z of G is a normal subgroup of G, we first need to show that the identity element of the group G lies inside Z of G. As we have already discussed earlier, the identity element commutes with every other element of the group, and therefore the identity element lies inside Z of G. Second, we need to prove that Z of G is closed under the group multiplication operation. That is, if we take any A and B inside Z of G, we must show that AB is also in Z of G. Notice that if we have A and B inside Z of G and any X inside G, then AB times X will be the same as A times B of B times X. But since B is inside Z of G, B times X is the same as X times B, and therefore we get A times XB. Again, using the derivative of the operation of the group, we have AX times B, and since A is inside Z of G, we have XA times B, which is equal to X times AB. So we have shown that given any X inside G, AB times X is equal to X times AB, which proves that AB lies inside Z of G, and therefore Z of G is closed under the group multiplication operation. Next, we need to show that Z of G is closed under taking inverses. So let us start with any A inside Z of G. And any X inside G. Here, as A is inside Z of G, we know that A times X is the same as X times A. Multiplying throughout on the left by A inverse, we get x is equal to A inverse xa, and therefore multiplying throughout by A inverse on the right, we have x times A inverse equals A inverse times x, and therefore we have proved that A inverse commutes with every element of G, and hence A inverse belongs to Z of G. This proves that Z of G is a subgroup of G. Now, let us prove that Z of G is a normal subgroup of G. To prove that Z of G is a normal subgroup of G, we need to prove that Z of G is closed under conjugation. In the sense, if we take an A inside Z of G and an X in G, we need to prove that X inverse AX is again in Z of G. Since A is in Z of G and X is in G, we know that A times X is the same as X times A. Now, multiplying throughout on the left by X inverse, we have X inverse AX is equal to A, but we all know that A lies inside Z of G, and therefore we have shown that given any A inside Z of G and any X inside G, X inverse AX is inside Z of G, which proves that Z of G is a normal subgroup of G. Now, let us define the centralizer or normalizer of an element A in a group G. The centralizer or normalizer of an element A is the set of all those points G in G such that G commutes with A. If G is an abelian group, we know that the centralizer of A will be G itself. We can also observe that the identity element of a group lies in the centralizer of A, and thirdly, we can observe that given any integer n, A raised to n will be in the centralizer of A. That is because A raised to n times A is the same as A raised to n plus 1, which is the same as A times A raised to n, and therefore we see that A raised to n commutes with A, and hence the centralizer of A contains all the elements of the type A raised to n. Now we should ask ourselves a few questions. First, is C of A subgroup of G? Second, if C of A is a subgroup of G, is C of A normal subgroup of G? And thirdly, is there a relation between C of A and Z of G? This is a very natural question, as both of the sets deal with a similar property. Let us prove that C of A is a subgroup of G and the center of the group always lies in C of A. To prove that C of A is a subgroup of G, we first need to show that the identity element lies inside C of A, We have already given this argument earlier. So we know that E is in the centralizer phase. Next, if we take any two elements X and Y in the centralizer of A, we should prove that xy times A is the same as A times xy. Let us see the argument for this. This argument is very similar to the argument used in Z of G. Notice that xy times A will be x times ay since y is inside the centralizer of A, which is the same as ax y, and therefore xy times A is the same as A times xy, which proves that xy is also inside C of A. Next, we need to prove that C of A is closed undertaking inverses. So let us start with an element x inside C of A. This argument is very similar to the argument that we have done for the center of the group. Here we see that x times A is equal to A times x. Multiplying throughout on the left by x inverse, we have A is equal to x inverse ax. Again, multiplying throughout on the right by x inverse, we have A times x inverse is the same as x inverse times A, which tells us that x inverse commutes with A and hence x inverse belongs to C of A. Therefore, C of A is closed undertaking inverses, and hence C of A is a subgroup of G. Next, let us prove that Z of G is contained inside C of A. To prove this, we start with any element x inside Z of G. Notice that as x commutes with every element of the group, in particular x commutes with A itself. Therefore, x times A is the same as A times x. And this tells us that x belongs to C of A. Therefore, the center of the group is always contained inside the centralizer of A. Now, let us show that C of A may not be a normal subgroup. To prove this or to show this, we need to give an example of a group G and an element A in G such that C of A is not a normal subgroup of G. Let us consider the group S4 and the element 1, 2 in S4. That is the cycle that takes 1 to 2, 2 to 1 and fixes the elements 3 and 4. To prove that C of A is not a normal subgroup of G, we need to find an element x inside C of A and some element y inside G such that y inverse xy is not in C of A. Let us consider the element in C of A. Let us consider the element which we are very well aware is in C of A, that is A itself. So in this case, we are going to take x to be A, and let us take the element y in G to be the element 1, 3. So what is y inverse AY? Y inverse AY is 1, 3 into 1, 2 into 1, 3. You can compute this and see that this is the permutation 2, 3. Now we will prove that 2, 3 is not in C of A. That is, we need to show that 2, 3 does not commute with 1, 2. What is 1, 2 into 2, 3? Here we see that 1 goes to 2 while 2 goes to 3 and 3 goes to 1. Therefore, 1, 2 into 2, 3 will be the permutation 1, 2, 3. Also, 2, 3 into 1, 2 is the permutation where 1 goes to 3 and 3 goes to 2. Since 1, 2, 3 and 1, 3, 2 are not the same permutations, we see that 2, 3 does not commute with 1, 2 and hence C of A is not a normal subgroup of G. Next, let us prove that if G by Z of G is a cyclic group, then G is abelian. As G by Z of G is a cyclic group, we know that G over Z of G is generated by a single element in G by Z of G. We know that the elements in G by Z of G are left cosets of Z of G, that is, elements of the form A times Z of G. Let us say that G by Z of G is generated by A times Z of G. Now, to prove that G is abelian, we first start with two elements, say X and Y inside G, and we need to prove that X times Y is the same as Y times X. Since X and Y are inside G, X times Z of G and Y times Z of G will be in the set of all cosets of Z of G. But the set of all cosets of Z of G, as we have assumed, is a cyclic group generated by A times Z of G. Therefore, there is some M and N inside Z, set of integers, such that X times Z of G is equal to A raised to M times Z of G, and Y times Z of G is A raised to N times Z of G. This tells us that X belongs to A raised to M times Z of G, and Y belongs to A raised to N times Z of G, which means that there exist some Z1 and Z2 in Z of G such that X is equal to A raised to M times Z1 and Y is equal to A raised to N times Z2. This means that X times Y will be equal to A raised to M times Z1 into A raised to N times Z2. Since Z1 is in Z of G, we see that Z1 commutes with A raised to N, and therefore we have XY is equal to A raised to M times A raised to N Z1 into Z2, which is A raised to M plus N times Z1 into Z2. Also, we can observe that Y times X is A raised to N times Z2 into A raised to M times Z1. Now, as Z2 is in Z of G, Z2 and A raised to M commute, which gives us A raised to N into A raised to M times Z2 into Z1. This gives us A raised to N plus M, which is the same as A raised to M plus N into Z1 into Z2. As Z1 and Z2 are in Z of G, we know that Z2 times Z1 is the same as Z1 times Z2. Hence, we observe that XY is the same as YX. And hence, we have shown that G is an abelian group. Therefore, if G by Z of G is a cyclic group, then G is an abelian group. Keep note of this theorem. We will use it often during the course.